Hello everyone, I'm Li Zhihan from Southeast University. It's my honor to present my paper, Learning-Based Eco-Driving Strategy Design for Connected Power Split Hybrid Electric Vehicles at Signalized Corridors in Intelligent Vehicles Symposium. In general, we proposed a hierarchical control structure for power split hybrid electric vehicles to achieve multi-control objectives. Today, my presentation will be introduced from the following four aspects. Firstly, we will discuss the research background. HEVs eco-driving problem is basically an energy management problem, but considering speed planning. Take urban scenario for example. The vehicle can plan its speed to pass through several intersections without idling, which can improve traffic efficiency and avoid idling fuel consumption for the internal combustion engine. The solution to eco-driving is divided into a rule-based method, optimization-based method, and learning-based method. With the development of neural network, learning-based method is regarded as a good technique to solve high-dimensional problems, especially for connected vehicle driving in dynamic traffics. However, it is difficult to achieve real-time eco-driving control for hybrid electric vehicles, since the speed optimization and powertrain energy management should be solved simultaneously. Therefore, we proposed a hierarchical control structure to solve the ecological speed planning and optimal torque distribution respectively. Existing research usually focuses on series or parallel configurations HEVs and lack comprehensive consideration of energy consumption factors. Especially for power split hybrid electric vehicle, we should consider the powertrain dynamics for precise optimization. Thus, we introduced an equivalent fuel consumption model to train an agent through proximal policy optimization algorithm. It provides acceleration to the bottom energy management system. We applied an equivalent consumption minimization strategy, ECMS controller, in the bottom stage for real-time optimal torque distribution. Then I will introduce the methodology of this paper. Toyota Prius is a classical power split hybrid electric vehicle, which is selected as our vehicle model. Its hardware structure and vehicle's parameters are shown in the left, and its longitudinal dynamics and powertrain dynamics are shown in the right. In order to balance the computation and accuracy, we proposed a polynomial-based equivalent fuel consumption model to approximate energy consumption. We selected 7 different driving circles, including NEDC, FUDS, HWFET, etc., and adopt dynamic programming to solve the optimal control in these driving circles. We applied a constant equivalent factor with SOC penalty to convert battery energy into fuel consumption for each step. Thus, we can obtain the equivalent fuel consumption in different power demand, and finally use polynomial fitting to get an equivalent fuel consumption model. In traffic model, we ignore the yellow light for safety, and the traffic state function is shown in that equation. We assumed that the connected vehicle can only obtain the signal phase and timing information or speed information in the current intersection. The environment model is open access. If you are interested in it, you can get it in my GitHub. Not like traditional deep learning with labels, reinforcement learning needs to estimate state action value, and the advantage function is widely adopted. The loss function of the policy network or actor network in PPO is made up of the clip ratio epsilon and the advantage function A pi. PPO updates the policy within a trust region by the clip ratio, which guarantees the policy improved monotonously. The overall objective function is listed here and the constraint in right should be satisfied by the bottom controller. ECMS is a classical energy management method for HEVs. The selection of the equivalent factor affects the optimization quality. ECMS calculates the cost table under the current power demand and find the control output with minimized cost. We adopted a constant equivalent factor with SOC penalty to adjust equivalent fuel consumption. Then I will introduce the simulation and the simulation result part of this paper. The deep reinforcement learning training is carried out under PyTorch framework and a custom gym environment. The version of Python packages is listed here. The hyperparameter is shown in table, and we choose an 8,000 meters road in Nanjing with 6 intersections for training. We discretize the simulation in space domain. The reward function design is shown in left. The reward function consists of 5 aspects. We designed 2 different speed rewards to discuss the impact of vehicle speed on energy consumption. When we choose to use the upper one, the agent explores the speed within a reasonable range, which is lower than the speed limit and higher than a minimum speed. It has the potential to get less fuel consumption for its larger policy range. We called it energy-oriented. When we choose to use the bottom one, C2T, the reward depends on the distance between the current speed, Vt, and a target speed, VTAR. The target speed is generated by a rule-based planner. We call this reward function design as time-oriented. Obviously, the time-oriented agent cannot risk to explore more speed for its higher punishment. The mean reward curve is shown in right. Both of 2 agents achieve convergence, and time-oriented agent obtains higher mean reward for its smaller policy range. We use 2 reference strategies in upper planner to compare the performance of the reinforcement learning agent. The first one is a rule-based speed planner, or a GLOSA system in other words. It generates speed recommendation according to the current speed information, and uses an intelligent driver model to generate acceleration command. The second one is called Accelerate Constant Brake Strategy, or ACB strategy, which cannot receive speed information. It will accelerate the vehicle to the maximum speed in current road, and keep it constant until the vehicle has 300 meters left to reach the intersection. Then brake the vehicle to pass or wait. The trajectory of the vehicle is shown in right figure. All of these 4 strategies use ECMS as their bottom controller to calculate the actual fuel consumption. It can be seen from the velocity trajectory that even if the ACB strategy has idling, it has achieved the shortest travel time, because it accelerated the vehicle to the road speed limit. But its SOC decreased most and has the highest fuel consumption. Time-oriented agent has a similar velocity trajectory as the rule-based strategy, but it considers the equivalent fuel consumption when training, so it has a better fuel economy performance compared with the RB-IDM. Energy-oriented agents achieve at least 7.39% of fuel economy saving and avoid a significant drop in the battery SOC at the expense of higher than 5% of travel time. It should be noticed that there's a slow-down operation in the 6th section. Then the energy-oriented agent gets the highest travel time. To have a fair comparison, we adopted a fuel economy correction method to recalculate the fuel economy of PPO agents. The energy-oriented agent achieved 3.7 liters per 100 kilometer, and the fuel economy of time-oriented agent is close to 4.2. We also applied the agent to untrained scenario. The freeze delay of the speed information in 6 traffic lights are initialized randomly, and 500 tests are conducted. It can be seen that the time-oriented agent has similar travel time to the RBIDM, but still achieves 5.8% of fuel economy reduction on average. An energy-oriented agent achieves 11.98% of energy saving at a cost of 1.52% of travel time. In conclusion, this paper proposed a hierarchical control structure to solve the eco-driving problem for a power-split hybrid electric vehicle in urban scenario. Simulation proves that the proposed method has a great potential in energy saving. However, the safety risk of learning-based algorithms still exists when applying in the real world, and the potential of the reinforcement learning in the end-to-end control is not fully developed. In the future, we will overcome these shortages. Thanks for your listening.